Good evening. In this video, we'll be talking about Type 1 supernovas. Supernovas are nothing more than exploding stars. So, to start off, we need a star. Stars, more specifically young stars, are mostly made of hydrogen and some helium, the two most abundant elements in the universe. Stars are also incredibly hot and extremely pressurized, especially towards the core. So in order to create a Type 1 supernova, we'll need a moderately sized star. Let's take the Sun as our example. It is about 5,778 Kelvin, or about 10,000 degrees Fahrenheit on the surface of the Sun, but it's about 14 million Kelvin, or about 27 million degrees Fahrenheit at the core. So only in the extremely hot, highly pressurized core can a very special process occur: nuclear fusion. Nuclear fusion is the process by which lighter elements combine to create heavier elements. In most young stars, hydrogen is the fuel source. 4 hydrogen atoms combine to create a single helium atom. However, the mass of the helium atom is less than the combined mass of the 4 hydrogen atoms. The missing mass is actually the mass being converted into energy, described by the equation E equals mc squared. It is actually this energy that we perceive as light, heat, and the rest of the electromagnetic spectrum. However, what happens when the star runs out of hydrogen? Stars may be huge, but they are not infinite in size. Hence, stars, when hydrogen is exhausted, start using helium as its fuel source. Helium nuclear fusion starts to kick in, where helium atoms are combined to produce carbon. From the beginning of the star's life, hot gas pressure fueled via nuclear fusion has always been an outward force, and gravity always an inward force. Like yin and yang. The two are in perfect balance. The amount of energy the Sun pushes out is the exact same as its gravitational attraction in. However, this harmony can only happen if the star is running on hydrogen. Since the star is running on helium and not hydrogen, there is an imbalance. There are less helium atoms, and therefore, to keep the star from collapsing, the temperature of the core increases while it also shrinks. This makes it easier to have fusion into heavier elements from elements that are not hydrogen, but it also slowly makes the star expand into a red giant. The entire star inflates 1,000,000 times its original size. Since there are less helium atoms than hydrogen when the star was young, the helium star does not last very long. Eventually, so much energy will be produced that the stellar winds will eventually blow the outer layers of the star away into interstellar space, resulting in a planetary nebula. The core shrinks into a ball of oxygen and carbon called a white dwarf. White dwarfs are about the same size as the Earth. If the white dwarf is a single star, the white dwarf will glow until it cools itself, transforming the star into a black dwarf, a cold star emitting little or no light. However, if it circles another star, then the ending will be more spectacular. The white dwarf will accumulate materials that are deposited from its partner star in a process known as accretion. The white dwarf slowly gets heavier. Heavier the star, more unstable it gets. Eventually, the white dwarf will produce a classical nova. The nova is the result of the rapid fusion of the accreted hydrogen on the surface of the star, commencing a runaway fusion reaction. The white dwarf continues to gain mass, undergo a runaway fusion reaction, explode, and restart the cycle all over again. This cycle continues for thousands or even millions of years. Essentially, these stars are just bombs waiting to happen. Classical novae stop occurring only when the white dwarf approaches Chandrasekhar's limit, or about 1.4 solar masses. Once fusion has begun, the temperature of the white dwarf starts to rise. The white dwarf is unable to regulate the fusion process in the matter of normal stars, so it goes under a runaway fusion reaction. A portion of the carbon and oxygen in the white dwarf are converted into heavier elements within a period of only a few seconds, which raises the internal temperatures to billions of degrees. The energy forces the star to explode and release a shock wave roughly 6% of the speed of light. What remains after the explosion is the work of the star's entire lifespan. Iron is one of the main components of the blast, spewing iron light years away. It is this iron that we use in our skillets and in our blood. The star also gives a blast of gas, tinted with various colors. The collection of gases in one place is called a nebula. Many transparent gases on Earth actually exhibit color in the nebula. Hydrogen is a deep red, nitrogen a swampy green, and oxygen a watery blue in color. Nebulae contain all the elements that the star ever created in one blast of energy. This nebula is often termed as a supernova remnant. Sometimes, however, there are some binary stars that are extremely close to each other and which zip around the center of mass in terms of minutes. These sorts of stars are called AMCVNs. This is a type of cataclysmic variable and is something I've been doing a research project on recently. I have also been working on a project with the All-Sky Automated Survey for supernovas, or ASSASSIN for short, for the last 2 years. It is the only project that surveys the entire sky for transients, which of course include cataclysmic variables and Type 1 and Type 2 supernovas. With that, I end this video. Thank you and goodbye.